All right, so in this video, I'm going to talk about homothetic transformations. And I'm going to talk about centers of dilation, vectors, how all that stuff relates. And what is important is that a homothetic transformation is a special type of similarity transformation. So a homothetic transformation is an angle-preserving function. It makes things bigger and it makes things smaller. So that's what's important. So we're going to talk about a function that makes things bigger and smaller. So, and before I get into that topic, I'm going to have to talk about vectors more to allow you to understand this. So again, a vector is where you have, let's say you have a couple points in space. So let's say we have the point P out here, and you have the point Q out here. Now, a vector has a head, so there's the head, and there's the tail. And it's easy to conflate vectors with rays in geometry. So a vector is a finite thing. It's only going from P to Q. It's not like it's going on forever. A ray would be going on forever, and it has the same notation as well. So this would be denoted as the vector from P to Q. So that's how we would denote that vector there. All right, so we're talking about vectors here, first off. And again, we always, and this is kind of strange, but you just get in the habit of doing this. What we do is we define the vector from P to Q as being Q minus P, the point Q minus P. So let's say the point Q here was 7, 4. And let's say the point P was, all right, let's make it 1, let's make it 1, 2. What this means is the vector from P to Q is Q minus P. So it would be equal to, so Q is 7, 4. So I'm going to write 7, 4 minus P is 1, 2. So I'm going to write minus 1, 2. Make sure you have those. Very important. So you go. The vector from P to Q would be 7. So I'm just going to look at my x coordinate and my y coordinate one at a time. So I'm going 7 minus 1 is 6. So I write 6, 4 minus 2 is 2. So we see 6, 2. And what you should notice is that if I went from 1 to 7, in the x direction, I'm traveling 6 units to the right. And in the y direction, I'm traveling 2 units up. So we can kind of see a vector is really its x coordinate and the y coordinate. So it's telling us the difference in those values right there. Kind of hidden. All right, so we talked about that. Now I'm going to talk about the scale factor. So this is a vector, and we're going to talk about scaling and vectors. All right, so we're going to talk about scaling. And a lot of times, instead of just denoting the points P and Q, we could just denote a vector in space, V for vector. So this vector, it's always going to be finite. Let's say it's V, and it's written like that. So what I can do with that vector is I can scale it. I can make it bigger and smaller. So, and it's always going to be, so this is always going to be the base of the thing. And you're going to kind of make it bigger, or you can make it smaller, and you can also move it this way as well. You can go as long as it's collinear with it. So let's say this vector had a magnitude or a length. So I took a ruler and I measured the distance from here to here, and let's just say that distance was 3 inches. What I can do with that vector, and let's say I wanted to make this thing twice as big. So I wanted to make it twice as big. I can take that vector and make it twice as big by scaling it. So the new vector would be 2 times the vector v. And this length from here to here, that would be now 6 inches. Pretty cool that you can do it. So you can do that. Now, you can also take a vector and you can, and again, this vector is right here, right there. You can also take this vector here and you can swing it around this other way. And that happens when the vector right here has a negative number attached to it. So let's say I wanted to take this value and make it go all the way over here. So I'm wanting it to be the same length at 3 inches. What this vector would be is minus v. So we just took the vector and we attached a little negative right there. And so minus 2v would be all the way down here. So it's just making it bigger or smaller, so we can kind of see it. We can scale vectors that way. All right, now I'm going to talk about homothetic transformation. All right, so let's talk about a particular type of transformation, homothetic transformation. All right, now there's a lot of terminology with this. What is important is that, and we could prove this, it is a type of similar transformation. So that means that this transformation is an angle-preserving function. It makes things bigger and smaller. That's what's important about this. All right, so I'm going to tell you how to do this. So if you have just an arbitrary point, so P, and you're wanting it to be mapped to the point P prime, that's what the mapping is here. So we can represent this mapping here, and we do that for every single point. And this is the equation we use. So it's P prime is equal to, and use, so this is lambda, so like lamb like the animal, and duh like duh Mr. Garsky, that's lambda. All right, so it's a cool looking symbol, I know. All right, but try and use these symbols because they're commonly used, and it works out very nicely with this. So P prime is equal to lambda, and then remember CP/CTC? Well, it's almost like that. So it's CP, and it's the vector, and then plus C. And I'm going to tell you what all those objects are in this transformation here. The point C is said to be the center of dilation. So the point C is the center of dilation. We have our point P. So this is an arbitrary point in the pre-image. And this value right here, we're just going to call this thing our ratio. Might also see it written as the ratio of homothenity, but what's important is that this is the ratio right there. And what is interesting is that it is a type of similar transformation. This ratio can be negative. And remember, with our vector, we could take it and flip it. That's this flipping thing going on right here. This ratio can, in fact, be negative. However, this scale factor, which I talked so much about before, cannot be negative. It is never negative. And in fact, our scale factor, so the absolute value of lambda, is equal to our scale factor. So again, the scale factor cannot be negative, but the absolute value of our ratio will give us our scale factor. All right, now let's put this all into context. And this is our point that it's being mapped to. This is our point in our pre-image. I mean point in image. Image. So we're taking it in our pre-image, we're mapping it to our point in our image. All right, let's put it. All right, let's get an example going. So here's an example. Let's say I have a triangle. I'm wanting it to be mapped. Mapped in space. Let's say this triangle has points P, Q, and R. And for our benefit, let's just consider the point P here. You do this with every single point. Let's say the point P is 7, 3. And let's say the center of dilation is way over here. Let's say the center of dilation is the point, let's make it 1, 0. All right, so let's explain, I'll explain what this all means. So again, this is the center of dilation. And we're called the equation, in case you forgot it, P prime is equal to, I'm trying to remember, lambda. Okay, so there's that. And then CP, CT, okay, so CP plus C. Okay. All right, so we're putting everything together here. So what happens is this value is our center of our, so this is our center. So I'm going to take this value here and I'm going to look at a vector from here. So a vector from C to P looks something like this. This is our center of our dilation right here. Our vector from our center of dilation to here looks like that. That's CP. Now we can make this vector be bigger or smaller. We can flip it. So lambda could be negative. It could be over here. We can make it bigger. Lambda could be like 2. It could be, lambda could be 3. We can make this point be anywhere we want it to be. So let's say I just wanted lambda to be 2. So I wanted this vector here to just be twice as big. What happens is every single distance is going to be twice as big as well. It doesn't matter. So you think about it in the x direction or the y direction, this direction, it's going to be twice as big. So from C to P, let's say I wanted this vector to be twice as large. So from here to here, I'm just making it twice as big. We got almost right there. The point P prime would be about right here. All right, so this would be lambda times CP. That's that vector right there. And again, we're just going to say lambda is equal to 2. And that's about what lambda is. So where would the point P prime be located in space? And again, this whole triangle gets mapped in this way. So the triangle, every single point along it gets twice as big. But we're just focusing in on one point at a time here. So the point P prime would be equal to, so lambda here is 2, so I'm going to put 2. CP, all right, let's look at CP. The vector from C to P, that value would be, so C to P, you have to think about it backwards. So you're going P minus C. So I'm thinking about the vector here. P minus C. So it goes 7 minus 1 is 6. So I put a 6. 3 minus 0 is 3. So I put a 3. So that vector from C to P is 6, 3. So I'm going to write 6, 3 here. And then I have my plus C. Plus C. What's my center of dilation? My center of dilation is the point 1, 0. So I'm going to write make sure you have the parentheses around it. So it's 1, comma, 0. It's a point, so it's a tuple, so you need those parentheses there. All right, so the point P prime would be equal to, you multiply first, so you're going 2 times 6. It's order of operations. You multiply before you add. 2 times 6 is 12. 2 times 3 is 6. Plus 1, comma, 0. So the point P prime would be equal to 12 plus 1 is 13. And 6 plus 0 is just 6. So that point P prime would be mapped in space to the point 13, comma, 6. And this process can be repeated for any value in our transformation here. Notice what happens to the x-coordinate here. So this difference from here to here, so this is 6, right? So I'm starting here. I went over 6 units to the right. What happened was, since I went 6 units to the right, I'm going another 6 units to the right. So my lambda is 2, so I'm going 6 times 2 is 12. So 1 plus 12 is 13. So I'm ending up here. And if I look at my y coordinates here, I'm going, so this distance, I'm traveling up 3. So twice that would be 6. So instead of 3, I count up 6 units from here. So 0. So from here to here, all the way over here. So everything is being, the x coordinate and the y coordinate, it's becoming twice as large. You can kind of visualize it. You can count twice as large from this center of dilation right here.